All right, everyone. So I'm going to go over here in a narrated Zoom meeting what I went over in lab today about calculations for the ecosystem processes lab. So I'll go over that short little PowerPoint I made and then go through the calculations as well to determine chlorophyll density, essentially, and then also mass of suspended particles from our traps at the two sites. So let me go ahead and share my screen and I'll pull up that PowerPoint. All right, here we go. So first of all, our data, this is the PowerPoint I made earlier today. So I don't know if the data for these last two samples have been updated, but this is what is entered on our class Google Sheet. And so we have the sample ID. Those are the names that you all gave your samples, your filter papers. And I went in there and I coded them, whether they were from Sweeten Creek or Beachy Creek. So if you remember, we measured sample absorbance on the spectrophotometer at 664 nanometers, which is where chlorophyll, it's the wavelength in the spectrum that chlorophyll absorbs. Then we dialed it up to 750 nanometers and measured absorbance there. Then we acidified the extract in the cuvette and again took a reading at 750 nanometers and then 665 nanometers post-acid. We didn't need any dilutions, so that column may be deleted off of our class spreadsheet already. And then the final column there is stone area, because of course the area of the stones that we scraped chlorophyll off varied, and so we're going to want to standardize chlorophyll to the area that was sampled. So just a reminder of what we've done up to now. We brushed all the chlorophyll off of the rock into those little brown Nalgene bottles. We then brought those back to the lab and filtered them onto multiple filter papers for each sample. And then those filter papers went in the freezer. That lyses the cells and makes it easier for the chlorophyll to be extracted. And then the last thing that I did then was I took those filter papers out of the freezer and I put them back into those brown Nalgene bottles with 30 milliliters of 90% acetone. And so acetone is an organic solvent. Chlorophyll is an organic molecule, and so it dissolves in the acetone. And so the acetone is used to actually dissolve the chlorophyll that was in the filters. And so then we withdrew about 3 milliliters of that extract in the acetone, put it into the little cuvette, and put that into our spectrophotometer. So this is how one determines chlorophyll A concentrations. There are actually multiple photosynthetic pigments, but chlorophyll A is the primary pigment that aquatic periphyton use. So we can use this chlorophyll A as sort of a proxy for rates of primary productivity. So you can see there, this will give us chlorophyll A in micrograms, and we get that by multiplying 26.7 times the difference between two quantities. Okay, and one of those quantities is has to do with the measurements of absorbance before we added the acid, and the other one after we added the acid. And so the reason that we add the acid is to correct for the presence of other pigments that are the product of chlorophyll breakdown. And so they will also absorb at very similar wavelength to chlorophyll. And so they can cloud our results, no pun intended. So basically what we do when we add the acid, it breaks down the chlorophyll so that when we take the absorbance at that point, all we're getting are those phaeophytin pigments. So the E665A is basically telling us how much absorbance in that sample is due to these pigments, which are not chlorophyll. So then we can subtract that from the total absorbance, and of course what we have left is chlorophyll. So the whole reason we acidified the samples was to get an estimate of these other pigments in that extract. And the reason that we subtract absorbance at 750 nanometers from the readings at the wavelength that chlorophyll absorbs light is because there could be turbidity in our samples. And so if the samples are turbid at all, that will also absorb light at all wavelengths, not just 664. So with each of those steps, we subtracted the absorbance at 750 nanometers to get a reading corrected for turbidity. So yeah, just to put a bow on it then, calculating the chlorophyll involves multiplying by 26.7 the chlorophyll, the absorbance due to chlorophyll. And so again, that's this E664B minus E665A, which is an estimate of those phaeophytin pigment absorbances. Cool. So how would we go about calculating this from our class data spreadsheet? So let me go ahead and switch over the screen I'm sharing here, and we'll take a look at that. My apologies here. I've got a bunch of windows open. I got to figure out which one is going to get me where I need to go. There we are. Okay. So there is my Google screen, my Zoom screen, and here are our data. So again, these are our sample IDs here on the left. I believe that on our class data sheet now we have them coded by site. But just a reminder, Lone Survivor is the only one of these that was actually a clay tile that survived the experiment. But so you can see all these absorbances here. And, you know, this absorbance at 750 was pretty low in most cases. So not a whole lot of turbidity, but there was some turbidity going on there. So it's good that we corrected for that. All right, so we've got the two pre-acidification absorbances, then the two post-acidification absorbances. So what are we gonna want to do? Well, first we're gonna have to get this quantity E664B. So to get that, we're gonna write our little formula in here, and of course in Excel as well as Google Sheets, all formulas start out with equals. And so we're going to subtract the absorbance at 750 nanometers from the absorbance at 664. So we'll go equals parentheses, and then I'll click on that cell that I want to subtract from. In this case, it's B2 minus C2. Close my parentheses, hit enter. And so there is the quantity E664B. And then, you know, I can just drag the corner of that cell down for all of my samples. We'll just do it for one for now. So there we go. All right, and then the next thing we need is E665A. So we're going to do a similar thing, subtract absorbance at 750 nanometers from absorbance, in this case at 665 nanometers, and this is post-acid. So I'm going to say equals, parentheses, E2 minus D2. So again, we're subtracting that turbidity correction, right? So there's a number. We'll grab the corner, drag it down, and we have it for the two samples. All right, well then we just have to take the differences in those two, right? So we want E664B minus E665A. So I'll just go equals, parentheses. Here's a value for E664B. Going to subtract a value for E665A. Close my parentheses, enter, there we go. Grab the corner, drag it down. All right, and then the next step is simply to multiply that value by 26.7. So I'll type in the number, well, I'm sorry, it equals there for the formula, 26.7 times, I don't know if I need parentheses here or not, so I'll just try it without, times that quantity there. Hit return, there we go. And drag it down. I just want to make sure. Yeah, that number's right. Okay, good. Yeah, so these numbers are about what we saw in lab earlier today. So it's about 2.5 times as much chlorophyll from the IV sample, which if I look back at my PowerPoint, which you can't see because I'm not sharing that screen. So I look back at the IV sample. IV was from Beachy Creek and Brick was from Sweeten Creek. So for this, these two samples at least, we looked to have more chlorophyll at Beachy Creek. But again, we need the area of the stone because, of course, stones with larger area, we would expect to have overall more chlorophyll. So we can go over to our, I think it's the chlorophyll data tab, is that right? There it is. And you see we have stone area in square centimeters. And these numbers are actually remarkably close. So we'll highlight that. I'll hit Control C, which will copy the value from IV. And I'll paste it in here. So there's the value for the area of the stone for IV. Then we need brick. And so there's the area for brick. And I picked the two that were almost identical. So if I come on over here and enter that, there you go. Cool. So now this number right here, the 0.64 and 1.63, that is the micrograms of chlorophyll A in the sample. And so to get the chlorophyll A per area, then we come over to column K, click on it, and we'll hit equals. And then we'll click on our chlorophyll A number here, divided by our area here, close the parentheses, hit enter. There we go. Drag it down. And there's our number. Okay. And that's how you do the calculations right there. So you can just go ahead and do them for the rest of the samples. As I said, we were waiting on 2 more. Hopefully we have those in there by now. And those are what you will need to go ahead and compare your chlorophyll. And I'm gonna come over and take a look at the paper, the document that describes what you need to do for the lab in just a second. But first, I'll finish up what else we needed to do on our Google Sheet. So yeah, so that's how chlorophyll works. I hope it's pretty straightforward. And the one thing I mentioned was that you might want to look and see if lone survivor, which is the clay tile, had values vastly different from the other ones, in which case you might want to leave it out since it's an outlier. But someone was doing the analyses and it looked like it didn't. So so yeah, I just leave it in there then. What the heck? All right. So the other piece for this lab is the suspended sediment data. So you can see the way they're set up here. We recovered 3 of our sediment traps, our yeah, our water column particulate matter traps. We've recovered 3 of them from Beecher Creek, only 1 from Sweeten Creek. And so you can see we have the size fraction for each of those samples. That's just the mesh size of the sieve that the particles were captured on. Then we have the weight of the Tupperware that the particles were put into, and then the final weight, which is dried weight. And that includes also the Tupperware container. So what we'll need to do then to find out how much of this final weight, dried weight, is actually due to the sediment particulate particles themselves, of course, is we'll have to subtract those. So I think you probably know how to do that. I just come on over into F here and, you know, just work in columns, right? Use the strengths of Google Sheets, which is essentially doing your calculations column by column for you, and you know, subtract the Tupperware from here to get the final, to get the weight of just the sample. Okay, cool. So let me go ahead and stop sharing this screen and go back to our PowerPoint just briefly. So we went through all this already. Chlorophyll. Now, I ask you to create a graph for the suspended particles. And I asked you what that graph might look like because I ask you to make a graph that will make it easy to compare the different samples for a given particle size. And so, you know, I made something like this. These are not real numbers at all. In fact, they're not even close, but I just wanted to show kind of what this would look like. And so you can see on our x-axis, we've got the different size fractions and micrometers of the sieves. We've got the mass in grams of samples on the y. And then we have our samples entered here so that for each size fraction, we can compare the amount in each sample. And a couple people did the calculations. It looks a lot different from this. But when you set it up this way, it allows you to very easily say, okay, you know, we've got 3 samples from Beecher Creek and 1 from Sweeten Creek. How does the amount of the smallest size fraction compare? How does the amount of the largest size fraction compare? And I didn't ask you to do any statistics on the sediment. Just make this graph, kind of look at it, and you know, try to kind of tell the story from it. So I went ahead and you know, we'll take off the title that Excel or Google Sheets gives us automatically, and we'll add a figure legend on the bottom. All right, so I'm going to stop sharing that. And the last thing I'm going to do is just real briefly look at our paper guidelines. So again, similar to the first, you know, first paper is written in scientific paper format. There are a couple resources I've added onto our Moodle page under a different topic, but as I said in lab today, you may be able to incorporate some of those same references that I put on there for your first paper as well. So as far as what I'd like you to present in analyses, I've written them out here, and I will post this on Moodle after I finish this this recording. But you know, so here are the steps to calculate chlorophyll, which you know, we went over on the PowerPoint and then on Google Sheets. We did this as well, standardizing it by area. Then, similar to what we did in the first lab with percent EPT and FBIBI, I'd like you to calculate mean and standard deviation chlorophyll A per stone area for each site. So essentially the chlorophyll A concentration, if you will, for each site, right? So present the mean and standard deviation, just like the graph that you had of percent EPT or of FBIVI from the last the lab, the community composition lab. Similarly, I would like you to use a t-test again to test for significant differences in chlorophyll A concentrations between the sites. You know, so you'll have 4 samples for each, and the syntax for that t-test is in the video before, but it's the previous lab video, but it's really straightforward. You just type in into Google Sheets equals t-test, all one word, parentheses, highlight your first array, say your 4 samples from Beechtree Creek, comma, highlight your second array, the 4 samples from Sweeten Creek, comma, and then someone thought the next options are 2, 2, because then you need to select the options for a two-tailed test, because we want to know if either one is greater than either one. And then also the equal variances option. So the syntax should be equals t-test, parentheses, highlight one array, comma, highlight the second array, comma, 2, 2, and parentheses, hit enter. That'll give you the p-value for the t-test comparing the two. And then number 5, for our suspended particles, we just went over how to calculate the mass of that for each of the 4 samples. And then I'd just like you to present those data in a graph that will allow us to look at it and see if there are big differences between Sweeten Creek and Beechtree Creek. And then, of course, in your results, you'll write a narrative that refers to those graphs and essentially describes the results, says what we found. So I hope that helps. I hope I think there's probably a little less work on the analysis side for this paper than the first paper, but as always, let me know if you have any questions at all. My kind of standards and expectations for scientific papers, you know a little bit by now from my feedback on your first paper, but I also have the scientific paper pointers handout posted on Moodle, and that talks a little bit in detail about each of the sections. So if you're unclear about what I'm looking for in each section, you can just go and check out that handout on Moodle. So happy analyzing. I'll look forward to reading your papers. And like I said, let me know if you have any questions at all, and good luck.